Hello everyone, welcome to our presentation. My name is Zhiwen Cao. This work is done by collaborating with Zongchen Chu, Dongfang Liu, and Yinjie Chen. Today, we're going to talk about using a new vector-based representation to enhance head pose estimation. Head pose estimation has many applications. It can be used in driver monitoring system, human attention detection, and to help improve many other tasks. We note two potential issues exist in current researches. First, most datasets for head pose estimation are annotated by Euler angles, pitch, yaw, and roll. As shown in the image, we can find that these similar profile images have very different pitch and roll angle labels. This is because Euler angles are discontinuous, and this will make it extremely difficult for a neural network to learn. In fact, other representations, which are less than 5 dimensions, including quaternions, are also discontinuous. Second, this discontinuity also makes mean absolute error of Euler angle, which is widely used for performance evaluation, not accurate, especially for these profile views. Our contributions can be divided in two parts. First, we reformulate head pose representation using 3 column vectors from rotation matrices, which form a continuous spatial orthogonal group. If we look at the unit vector label here, every element now is close to each other, and then we can also easily tell that this representation is preferable. We also put forward a new metric to replace MAE, the mean absolute error of vectors. For each column vector, we compute the angle difference between the ground truth and the predicted one. Then we obtain MAE by averaging the errors. The main structure of our network consists of a backbone and 3 head branches. Each head here is responsible for predicting 1 column vector. We define 3 stages, and at each stage, a feature mapping is extracted and fed into the feature mapping module for aggregation. Then the prediction module takes the aggregated features as inputs and make the predictions by averaging the outputs over all the stages. Our goal is to optimize the total loss, which is composed of regression and orthogonal loss. Regression loss calculates the mean square error of 3 vectors, and orthogonal loss calculates the cross product of each pair of vectors. This will help balance the errors of all 3 vectors together. Since the 3 vectors that our network predicts are not perpendicular to each other, we obtain the closest rotation matrix R from the outputs R hat by minimizing the Frobenius norm of R minus R hat. Its optimal solution can be obtained through singular value decomposition. We here plot the error distributions of different methods. All of them are trained on the dataset of 300 WLP and tested on AFL W2000. Our method, the green line, has smaller prediction errors, especially for large pose angles. This conforms to our explanation before. These are some prediction results of different methods. As shown in the second and third row of the image, these 2 Euler angle-based methods have very large errors. They fail to capture the visual pattern because the discontinuity of Euler angles. We can also illustrate it by an example. Assume a person now with yaw angle of 89 degrees. If he increases by 3 degrees, this causes no observable difference in image. However, to avoid gimbal lock, the yaw angle is not allowed to surpass 90 degrees. Then his yaw angle will become not 90 degrees, but 88 degrees instead. And this causes very large change in pitch and roll degrees. With the introduction of 3 vector representation, this change will become continuous. Thank you all for your attention. Please check out our paper for more details.